When we collect qualitative data from two or more independent populations, it's common for us to ask the question, do all of these have the same frequency distribution? Is the population distribution that characterizes how many individuals or what proportion of individuals fall into each of our categories, is that going to be the same across the populations? Or is there some difference? Right? If we were trying to compare the similarity of any two populations and the main feature that we care about is a qualitative variable, this is exactly the kind of question that we want to ask. And in this case, one of the ways that we can go about answering this question statistically is to use the chi-squared test procedure, and specifically to test the hypothesis of homogeneity of these populations. And so homogeneity is referring to a similarity or the sameness between multiple different populations. And so if we want to run the chi-squared test for homogeneity, what we're saying is we have multiple populations. We want to see, is the frequency distribution going to be equivalent across the different populations, or is there going to be differences that we can detect in our data? So the chi-squared test for homogeneity provides a technique for assessing whether two or more separate populations, independent populations, share a frequency distribution for some specific trait. So how does that test procedure actually work? Well, there's a desire to test whether two or more independent populations, and again, that assumption of independent populations is going to be sort of critical for us, have the same frequency distribution. The null hypothesis is that these distributions are homogeneous, so that they are the same. The alternative is that they are not. The observed frequency distribution is going to be denoted as OIJ, where I is going to characterize each population. So we have I1 up to IK. We're testing K populations. And the trait that we're testing is going to have L total categories, right? And so then we have OI1, OI2, up to OIL. Okay, and so for each population, we're going to have those L categories, and they correspond to the same things across all of our independent populations. Now, our expected value is going to be given by EIJ, right, corresponding to OIJ, and that's going to be equal to NI dot times by N dot J divided by the total number N. And so by way of notation, NI dot is going to be the sum of all the individuals who are in the first or in the ith population, rather. So what we take is we take OIJ and we add up across this second index here of J. Right, so we're adding up all of the values for J, so that's going to be J1 to L, right? So when we place a dot there, what we mean is we're going to take OI, we fix the I, and we add up over the J, okay? Similarly, N dot J is going to be fixing this J here if we add up across all the different populations. And so correspondingly, the NI dot and the N dot J are going to correspond to our column and our row totals, right? So this is the marginal total in the row, marginal total in the column, or vice versa, depending on which way you're writing this out. But those two marginal totals multiplied together divide by the overall total. Okay. The test statistic is then to take the sum of all of our observed values, subtract off all of our expected values, square that, and then divide by the expected value. And so again, we're summing over both of these indices, but we can think about this as just summing this up over the whole contingency table that we're looking at here. And if the null hypothesis is correct, then this test statistic here is going to follow a chi-squared k-1 times L-1 distribution. And so then we can use that as our null distribution to derive our p-value. The p-value is going to be the upper tail p-value here. And so specifically taking f of k-1 times L-1 to be the CDF of our chi-squared right here, then it's going to be 1 minus the CDF at whatever value we've actually observed. Okay, so the overall test procedure is the standard chi-squared test procedure with the hypothesis that the individual distributions are actually the same, that they're homogeneous across the various populations we're looking at. So we can take a look at some examples then of how this test procedure works out in action. Right, in this first example, we have a pharmaceutical company. They're testing a new drug designed to reduce the severity of migraine headaches. They want to determine if the effectiveness of the drug is consistent across different age groups. So these different age groups here, those are going to be our populations. The effectiveness of the drug is going to be what we're actually measuring. So the outcome is measured as either significant improvement or no significant improvement. Okay, and so we have our table written out here. Each of these rows is going to correspond to one of our populations. Each of these columns is corresponding to the individual trait. Right? We can write this out in whatever way is convenient for us. And so what we find is that there are 125 young adults, 75 middle-aged adults, 200 older adults. Okay, and then 250 total people had a significant improvement, 150 people had no significant improvement, right? And then the individual joint observations are given throughout, a total sample size of 400. We want to test if these populations are actually homogeneous at the alpha equals 0.05 level of significance. And so here, right, we're testing, is this distribution, the frequency distribution corresponding with our first row, really the same as this distribution corresponding to our second row, really the same as the distribution corresponding to the third row here, right? Are these three distributions actually all the same, or are there differences between them? Okay, and so that's what we want to determine. And so in order to do this, we are going to sort of start with the null hypothesis that they really are the same, right, versus the alternative that they're not. And then to find our expected values, well, we're going to need to calculate these 6 different expected values, right? And to get each one of them, we're going to take the marginal total for the row, multiply by the marginal total for the column, and then divide by this 400 here. And so 250 times 125 over 400, that is going to give us our first expected value. Then we could take 250 times 75 over 400 to get the second one, 250 times 200 to give us this one over here, and so forth, right, throughout the whole table. And so there's those 6 values we're going to want to compute, and then we can turn that into our chi-squared test statistic and go from there. Okay, and so in this case, we have the individual calculations actually being done, right? So 125 times 250 over 400, that's our 125, 250 over 400 to give us our expected value here. We have our 75 times 250 over 400 for our second one, 200 times 250 over 400 for the third one, and then we replace that 250 with this 150. So 125 times 150 over 400, 75 times 150 over 400, and 200 times 150 over 400, right? And so that gives us all of our expected values here, right? We have our 6 different ones, and then we're going to want to calculate out that chi-squared test statistic. And so sort of seeing those differences, right, to actually calculate out the differences, we're doing this, again, turn by turn. So we take our 80 minus 78.125, so that's our observed minus expected, observed minus expected, observed minus expected, and so forth through all of the different observations here, right? And so taking those 6 different differences, this is going to give us our individual differences. Now, what we should always find whenever we're doing these test procedures, and so this is a good way to check to make sure that you've gotten things right, we should find that the columns and the rows both sum to 0. And so if you look at this first row, 1.875 minus 1.875, right, that's going to give us a 0. Same thing here, and then same thing here. And same thing if you were to sum up the columns individually, right? So you're going to get a 0 if you sum all of these columns. And if you've done that, then you should find that things are actually correct with your differences, or at least there's not an obvious mistake that's been made. So once we have these differences, right, what we're going to want to do is we're going to want to take all the differences, we square them, and then we divide by each individual expected value. Okay, and so we can write this out in full here. So we take 1.875, which is this first difference, squared, divide that by 78.125, which is the expected value here. And then we're going to take negative 1.875, which is coming from right here. We square that, divide that by 46.875. And so that's going to be our expected value here. And we continue that process through all of the different observations that we've made here. Okay. And once we've done that all, we find a 14.72. Okay. So with that 14.72, we know that this should be coming from a chi-squared k minus 1 times L minus 1 distribution. And so then we would be taking 3 minus 1 times 2 minus 1, which is actually just going to give us our 2. Okay, and so we can work out under this distribution, right? We have our 3 minus 1 times 2 minus 1, which is our chi-squared 2 distribution. And therefore, the p-value is the probability that the chi-squared value is greater than 14.72, which is 1 minus the CDF at 14.72, and that's going to give us 0.0006. Okay, to find that 0.006, we can use the p chi-squared function in R. That's going to correspond to the CDF that we have here. Okay, so that's the 14.72, and the degrees of freedom equaling 2, all plugged in here. All right, and so from here, we can then draw our conclusion, right? So since the p-value is going to be smaller than our level of significance, we reject the null hypothesis and conclude that the populations are not homogeneous with respect to the impact of drug severity on the migraine headaches. There is a statistically significant difference in the frequency distributions of improvement versus no improvement between the various age groups. Again, we don't necessarily know what is that difference, but we can say that the drug works differently whether you're looking at young adults, middle-aged adults, or older adults. Okay, and so that's going to be a significant difference. Those are not homogeneous with respect to this specific drug. Take a look at a second example here. So in this example, a psychologist is interested in whether the patterns of social media usage differ across the various age groups. They hypothesize that younger adults may exhibit different preferences for specific social media platforms compared to older adults. And so once again, we divide up our population into young adults, middle-aged adults, and older adults. And then we have sort of this ranking as to which platform is their primary social media platform, platform A, platform B, or platform C. Okay, and so again, we have the exact same setup that we were looking at before. This is going to be a similar way that we're going to run through this test. Okay, so in this case, we're actually going to need to calculate 9 expected values, one for each of the population platform intersections, but each of those is going to be given by the marginal totals multiplied together divided by the overall total, right? So for instance, we could take this 140 here multiplied by 200 divided by 500, and that'll give us our expected value here. And then run through 140 times 150 divided by the 500 for here, 140 times the 150 for the expected value here, and so forth, right? Through the 9 different values. We're then going to take the differences between those tables, compute our test statistic, and go on from there. So let's walk through the specific values here, right? In this case, it's going to be mostly just a matter of keeping track of the calculations. When you're doing these calculations, I typically find that it's easiest to continue to draw out the tables so that you know exactly where the calculation is corresponding to. But whatever way you can keep track of the calculations is going to be helpful for you. So first, to get our expected cell counts here, okay, once again, we take our marginal totals, so 200 times 140 divided by 500 gives us this expected value of 56. 200 times 180 divided by 500 gives us our 72 here. 200 times by 180 divided by the 500 gives us the 72 here. Okay, and so we go through all of the different values here, and what we notice is that because this 150 and this 150 are the same, these two rows are actually going to be exactly identical to each other, and because this 180 and this 180 are the same, these two columns are actually going to be identical to each other. And so there's not as many calculations as it might originally seem, right? But we can get out our values in that way. All right, and so from here, we have our expected values. We want to subtract off the expected value from the actual observed value. Okay, and so that's going to give us these observations here, right? So we have a observed minus expected to give us out these different values in this case, right? Observed minus expected across all of them. And so then once again, what we should always find is that if you were to sum up the columns or the rows in this table, you should get a 0, right? So 24 minus 2 minus 22, that gives us their 0. 24 minus 22 minus 2 also gives us our 0, right? And so you should find the zeros across the board in these columns here. So once we have our differences, we now need to plug into our chi-squared test statistic. Okay, and so the chi-squared test statistic, again, is going to go through each of these. 24 was the difference, so we take 24 squared, divide by the expected value of 56 here. Then we take negative 22, square that, divide that by the expected value of 72. Negative 2 squared divided by 72, right? Negative 2 squared divided by 42, 6 squared over 54, negative 4 squared over 54, negative 22 squared over 42, 16 squared over 54, 6 squared over 54, right? We add all of those values up, and then we find that that should be 35.05. Okay, and so that's going to give us our chi-squared value. Here, we need to ask, well, what is the null distribution going to be? Remember, that's always going to have degrees of freedom k minus 1 times L minus 1. So 3 minus 1 times 3 minus 1, which is going to give us a chi-squared 4 distribution. And so now we can get our p-value as 1 minus that CDF at the 35.05 we've actually calculated. So the probability that our test statistic is greater than or equal to 35.05 is 1 minus the CDF at 35.05, which is going to give us this value, which is approximately 0 here, right? To get this value, we can actually turn to R, and in R, we're going to be using the p chi-squared function. Degrees of freedom is 4. We plug in our test statistic value of 35.05 here, okay? So then what is our actual conclusion? Well, since the p-value is going to be much smaller than the level of significance, we can reject the null hypothesis and conclude that the populations are not actually homogeneous with respect to their level of social media usage. So there's a statistically significant difference between the platform use, whether we're talking about young adults, middle-aged adults, or older adults. And so there actually does appear, based on the data we've collected, to be a difference in the usage patterns for these different age groups. Okay, and so the chi-squared test of homogeneity is going to be a standard chi-squared procedure, and it's used to test whether two or more independent populations share a frequency distribution for a specific trait. Again, I'll re-emphasize that independent populations is going to be critical importance here. Right? It's really what makes the homogeneity test unique to itself. Okay, we're thinking about having taken a random sample from multiple different independent populations. Using those random samples, we have our observed values, we calculate the expected values and go forth with that, but we are thinking about separate, distinct populations in this case. And so this is going to make it stand apart from many of the other chi-squared procedures that you might want to consider for other situations, which are relevant to a single procedure. But given the data from multiple independent populations, we can then run this chi-squared test procedure and ask ourselves, does this seem to support the thought that they're actually homogeneous, or do the distributions actually appear to be different between the different populations?